You are looking into the past right now. Not minutes, not years, billions of years. The light from distant galaxies takes so long to reach us that every telescope is really a time machine. When astronomers point a telescope toward deep space, they are not just looking far away. They are looking backward through cosmic history, and the deeper we look, the younger the universe should appear. Picture a city just after it has been built. The roads are empty. The buildings are small. Everything is still under construction. The early universe should look like that. Small galaxies, simple structures, young stars just beginning to form. That was the expectation for decades. But when the James Webb Space Telescope opened its mirrors and looked deeper than any telescope before it, something strange appeared in the darkness. Galaxies. Huge ones. Bright, massive, fully formed. And they were sitting in a time when the universe was supposed to be far too young to build them. At first, scientists thought it was a mistake, but the more they looked, the stranger the universe became. Because these galaxies should not exist yet, and their discovery may be forcing scientists to rethink how the universe grew up. You are moving through space right now. Not slowly, very fast. Earth is spinning beneath your feet at more than 1,000 miles per hour. At the same time, our planet is circling the Sun at nearly 30 kilometers every second. The Sun itself is traveling around the center of the Milky Way galaxy, and all of it is happening while the universe continues to expand. Yet none of this motion feels obvious. The ground feels still. The sky looks quiet. But when scientists point powerful telescopes toward the darkness between the stars, they begin to notice something remarkable. Space is not just a place. It is a record of time. Every beam of light moving through the universe carries a message from the past. Light does not travel instantly. Even though it moves incredibly fast, it still needs time to cross the enormous distances between galaxies. Think about lightning during a storm. You see the flash first, then the sound arrives later. The delay tells you how far away the strike happened. In space, the delay is measured not in seconds, but in years. When sunlight leaves the Sun, it takes about 8 minutes to reach Earth. The light from Jupiter needs roughly 40 minutes to arrive. The nearest star beyond our solar system sends its light across more than 4 years of space before it reaches us. And distant galaxies? Their light travels for billions of years. Picture this for a moment. Imagine taking a photograph of a city skyline. Now imagine that the photograph takes billions of years to develop. By the time the image appears, the city itself might have completely changed. That is how astronomy works. When we observe distant galaxies, we are not seeing them as they are today. We are seeing them as they were long ago, when the light first began its journey toward Earth. In other words, telescopes allow scientists to look backward through time. The deeper we look into space, the further back into cosmic history we travel. For decades, astronomers built instruments designed to push this boundary further and further. Each new telescope opened another window into the past. Ground-based observatories revealed galaxies billions of light years away. Then space telescopes began extending that reach. One of the most famous was the Hubble Space Telescope. Launched in 1990, Hubble changed humanity's understanding of the universe. Its deep field images showed thousands of galaxies packed into tiny patches of sky that once appeared completely empty. Those observations proved something astonishing. The universe was far more crowded than anyone expected, but Hubble still had limits. Even with its powerful mirrors, the telescope could only see so far into the early universe. Eventually, astronomers reached a barrier. The earliest galaxies were simply too faint and too distant for Hubble to detect clearly. The reason had to do with how light behaves over time. As the universe expands, the light traveling through it slowly stretches. Its wavelength becomes longer, shifting toward the red end of the spectrum. Scientists call this process redshift. The the farther a galaxy is from us, the more its light stretches during its journey. Over billions of years, visible light from very distant galaxies can stretch so much that it moves into the infrared range. This means that to see the earliest galaxies, scientists needed a telescope that could detect infrared light with extreme sensitivity. So engineers and astronomers began designing something new, a telescope unlike any built before. After decades of planning, construction, testing, and delay, that instrument finally launched into space in December of 2021. It was called the James Webb Space Telescope. Webb is enormous compared with earlier space telescopes. Its main mirror stretches over 6.5 meters across and is made of 18 hexagonal segments coated in gold. The mirror folds during launch, then slowly unfolds once the telescope reaches space. But the mirror is only part of the story. Webb also carries a giant sunshield the size of a tennis court. This layered shield protects the telescope from heat and sunlight, so its instruments can remain extremely cold. Cold temperatures are essential because Webb is designed to detect faint infrared light. Even a small amount of heat from the telescope itself could overwhelm the signals coming from distant galaxies. So Webb floats far from Earth, nearly 1 million miles away, in a region of space where the gravitational pull of the Sun and Earth balance in a delicate dance. From that distant location, the telescope quietly observes the deep universe. Now pause for a moment and picture what that means. A machine built by human hands is sitting far beyond the moon, unfolding golden mirrors in the darkness and staring into space so deeply that it can see light that began traveling toward us more than 13 billion years ago. That light started its journey when the universe itself was young, not millions of years old. Hundreds of millions. In cosmic terms, that is almost the beginning. Scientists expected that Webb would reveal the first small galaxies forming during this early era of cosmic history. Tiny collections of stars, irregular shapes, chaotic structures slowly growing under the pull of gravity. That expectation came from decades of theoretical models and computer simulations describing how galaxies form. According to those models, galaxy growth is a slow process. Gas gathers gradually. Stars ignite one generation at a time. Larger galaxies appear only after many smaller ones merge together. Think of it like building a city. First come small houses, then streets, then taller buildings. The skyline grows slowly over time. The early universe should have looked similar, a cosmic landscape just beginning to assemble its first structures. But when Webb turned its mirrors toward the deepest regions of space and began collecting its first observations, something unexpected appeared in the data, something that did not match the models. Some of the galaxies in Webb's earliest images looked far too large, too bright, too mature. They appeared to exist at a time when the universe should still have been building its very first structures. At first, many astronomers assumed the explanation would be simple. Perhaps the galaxies were closer than they appeared. Perhaps the measurements were wrong. Perhaps something in the data processing created an illusion. But as the observations continued, the same strange pattern kept appearing again and again. Galaxies that seemed far too developed for such an early moment in cosmic history. If the measurements were correct, these galaxies would force scientists to rethink how quickly the universe began building its structures. And that possibility raised an unsettling question. What if the early universe grew up much faster than we ever imagined? Because the deeper Webb looked, the stranger the story became, and scientists were only beginning to realize how big the mystery might be. For most of modern astronomy, scientists believed they understood how the universe grew up. Not every detail, of course. The cosmos is far too complex for that. But the broad outline of cosmic history seemed clear. It was built from decades of observation, mathematical models, and powerful computer simulations. The story begins with the Big Bang Theory. According to this model, the universe began about 13.8 billion years ago, in a state that was extremely hot and incredibly dense. Matter, energy, space, and time all emerged together in a rapid expansion. In the first seconds, the universe was too hot for atoms to exist. Particles collided constantly, forming a dense fog of energy. But the universe was expanding. And expansion means cooling. As the cosmic temperature dropped, the first atomic nuclei began to form. A few 100,000 years later, electrons joined those nuclei to create the first atoms, mostly hydrogen and helium. At that moment, something important happened. Light was finally free to travel through space. Before that time, the universe had been opaque, like a thick fog where light could not move freely. Once atoms formed, the fog cleared. The first light of the universe began its long journey through space. Scientists still detect this ancient light today. It fills the universe as faint microwave radiation called the cosmic microwave background. Think of it as the afterglow of the early universe. When astronomers map this radiation, they see tiny fluctuations, slight differences in density across the young cosmos. These fluctuations are important because they acted as the seeds for everything that came later. Picture a calm lake during a light rain. Each raindrop creates small ripples that spread across the surface. At first, the ripples are subtle, but over time, they interact and grow more complex. The early universe behaved in a similar way. Those tiny density differences slowly grew under the influence of gravity. Where matter was slightly denser, gravity pulled more gas inward. As gas accumulated, those regions became even denser. Over millions of years, clouds of hydrogen gas began collapsing under their own gravity. And eventually, the first stars ignited. Astronomers often call this period the cosmic dawn. Pause for a moment and imagine what the universe looked like then. There were no planets, no galaxies like the Milky Way, just enormous clouds of gas scattered across darkness. Then the first stars appeared, bright points of light, forming within collapsing clouds. These early stars were likely very different from the ones we see today. Many researchers believe they were extremely massive, possibly hundreds of times heavier than our Sun. They burned hot and lived fast. Some may have exploded as supernovae only a few million years after forming, scattering heavier elements into surrounding space. Those elements later helped create new generations of stars, planets, and eventually the chemistry required for life. But the formation of galaxies, the massive structures containing billions of stars, was expected to take much longer. This is where gravity and dark matter enter the story. Modern cosmology suggests that ordinary matter, the atoms that make up stars and planets, accounts for only a small portion of the universe. Most of the mass exists in a mysterious substance known as dark matter. Dark matter does not emit light. It does not interact with radiation the way normal matter does. But it still has gravity, and gravity shapes the structure of the universe. Scientists believe dark matter forms invisible halos throughout space. These halos act like gravitational wells, pulling gas inward and creating the conditions where stars can form. Imagine building a city inside a valley. The valley itself guides where the roads and buildings will appear. In the same way, dark matter halos guide where galaxies eventually grow. Over hundreds of millions of years, gas falls into these halos. Stars ignite. Small galaxies form. Then gravity brings galaxies together. Two small galaxies collide and merge. Later, those larger systems merge again with others. Over billions of years, the universe slowly assembles the large spiral and elliptical galaxies we see today. The process is gradual, like streams flowing together into larger rivers, or small villages expanding into cities over centuries. Computer simulations of cosmic evolution reflect this slow growth. They begin with the early density fluctuations seen in the cosmic microwave background and simulate billions of years of gravitational interactions. These simulations consistently show a similar pattern. At first, small galaxies dominate the universe. Large galaxies appear later after repeated mergers and long periods of star formation. By the time the universe reaches a few 100 million years of age, astronomers expected to see only the earliest building blocks of galaxies, tiny structures, irregular shapes, small collections of stars forming in chaotic bursts, nothing resembling the massive galaxies we observe today. This expectation guided decades of astronomical research. Observations from earlier telescopes, including the Hubble Space Telescope, appeared to support this model. Hubble detected many distant galaxies that were small and irregular. Just as predicted, the deeper scientists looked, the younger the galaxies seemed to become, which made perfect sense. Looking deeper means looking further back in time, and further back means closer to the beginning. So when the James Webb Space Telescope finally began its observations, astronomers were excited, but they were not expecting a revolution. They expected Webb to confirm the existing model in greater detail. The telescope would probably detect the earliest faint galaxies predicted by theory, maybe slightly earlier than Hubble could see, maybe a little more detailed. But the overall story of cosmic evolution seems solid. The universe started simple. Small structures appeared first. Large galaxies grew slowly over time. That was the picture. Then Webb sent back its first deep images. And almost immediately, astronomers began noticing objects that did not fit the pattern. Some galaxies appeared surprisingly bright. Others looked far larger than expected. At first, scientists thought they might be misinterpreting the data. Distance measurements in astronomy can be tricky. A closer galaxy can sometimes appear similar to a distant one, if the light is distorted or faint. So researchers began checking the numbers carefully. They measured the redshift of these objects. They compared observations across different instruments. They ran new analyses, and the results kept pointing to the same unsettling possibility. Some of these galaxies truly existed when the universe was only a few 100 million years old, and they looked far too developed to belong to such an early time. If those measurements were correct, the early universe had built large galaxies much faster than the standard models allowed, which meant one of two things had to be true. Either the observations were misleading, or the universe itself had behaved very differently than scientists expected. And as more Webb data began arriving, that question became impossible to ignore. Because the deeper astronomers looked, the more strange galaxies they began to find. The first images from the James Webb Space Telescope arrived quietly. There was no dramatic announcement at first, no global broadcast, just scientists opening new data files and studying the results on computer screens. But within hours, something unusual began circulating among research teams. The images looked crowded. Pause for a moment and picture what astronomers expected to see. When looking extremely far into the past, the sky should become emptier. Galaxies should grow smaller and fainter the deeper we look into time. After all, the early universe had only just begun assembling its structures. It should have looked like the first scattered lights of a city at dawn. Instead, Webb's images looked more like a city already glowing with activity. Bright galaxies appeared where only faint ones were expected. Some showed clear shapes, some looked dense, and a few appeared surprisingly large. At first, researchers assumed there must be a simple explanation. Astronomers have learned to be cautious. New telescopes often reveal strange patterns that later turn out to be measurement errors or optical effects. So the first reaction was careful skepticism. Maybe the objects were actually much closer galaxies whose light had been distorted by gravitational lensing. Massive galaxy clusters can bend light like a giant cosmic magnifying glass, making distant objects appear brighter or larger. Or perhaps the redshift estimates were off. Redshift is one of the main tools astronomers use to measure cosmic distance. As the universe expands, light stretches toward longer wavelengths. The greater the stretch, the further the light has traveled. If Webb was detecting extremely redshifted light, that meant the galaxies must be very far away. and therefore very old in cosmic time, but small errors in measurement can sometimes lead to big differences in estimated distance. So scientists began examining the data more closely. They ran independent calculations, they compared different observation methods, they checked instrument calibrations. For a while, many researchers expected the mystery to disappear. That happens often in science. An exciting anomaly appears, researchers investigate carefully, and eventually the explanation turns out to be something simple. But this time, the anomaly refused to go away. The galaxies still looked massive, and they still appeared extremely distant. To understand why this was so surprising, imagine building a skyscraper. You begin with the foundation, then the lower floors rise. Only after years of construction does the building reach its final height. Now imagine flying over a city that supposedly began construction only a few months ago, yet somehow towering skyscrapers are already standing. That was the feeling many astronomers had when studying the Webb images. Some galaxies seemed too mature, too organized, too bright. One research group identified several galaxy candidates that appeared to exist only about 300 million years after the Big Bang. In cosmic history, that is extremely early. The universe was barely 2% of its current age. According to previous models, galaxies at that time should still be small clusters of young stars forming within primitive gas clouds. Instead, Webb seemed to be showing objects that looked much more developed. Some appeared to contain billions of stars. That kind of mass should take far longer to assemble. Now here is where things become even more interesting. Astronomers did not rely on just one observation. Multiple research teams studied Webb's early deep field images. They used different analysis methods, different software pipelines, different measurement techniques. Yet several groups reported similar findings. Large galaxies seemed to be present far earlier than expected. One of the earliest datasets came from a region of the sky known as SAMAX 0723, where Webb performed a deep field observation shortly after beginning operations. The image looked almost unreal. Thousands of galaxies appeared scattered across the field like glowing grains of sand. Some were nearby. Some existed billions of light years away, and hidden among them were candidates for some of the earliest galaxies ever observed. Picture this. Each small dot in the image is not a star. It is an entire galaxy, containing millions or billions of stars. Now imagine zooming into the faintest points in that field and realizing their light began traveling toward Earth more than 13 billion years ago. Those photons started their journey when the universe was still in its infancy. For scientists who had spent their careers studying galaxy formation, the Webb images felt both thrilling and unsettling. Thrilling because the telescope was clearly revealing structures never seen before. Unsettling because those structures did not match long-standing predictions. Some astronomers began wondering whether the brightness of the galaxies might be misleading. Young stars burn extremely hot and bright. If a galaxy were undergoing an intense burst of star formation, it might appear brighter than its actual mass would suggest. That possibility offered some hope that the standard models might still hold. But brightness was not the only issue. Some galaxies appeared surprisingly compact and dense, suggesting large amounts of matter packed into relatively small regions of space. In other words, the problem was not just how bright the galaxies were, it was how quickly they seemed to have assembled. Astronomers began running new simulations to see if extreme star formation bursts could reproduce what Webb was seeing. Some models could partially explain the brightness, but many still struggled to produce galaxies of that apparent size so early in cosmic history. At this stage, the scientific community entered a familiar phase. Investigation. No one rushed to declare that cosmology was broken. Instead, researchers began asking careful questions. Were the redshift measurements accurate? Could dust within the galaxies be affecting how their light appeared? Were gravitational lensing effects amplifying their brightness? Could early stars behave differently from the ones we see today? Every possibility had to be examined. Science rarely moves by dramatic revolutions overnight. It moves through careful testing, step by step, measurement by measurement. But as additional Webb observations began arriving, something became harder to ignore. The pattern was repeating. More early galaxies appeared. Some seemed even larger than the first candidates. Each new dataset raised the same unsettling possibility. If these galaxies truly existed when Webb suggested they did, then the early universe had built complex structures far faster than scientists believed possible, and that meant the investigation was only beginning, because the next step was to determine one crucial detail: exactly how far away these galaxies really were. Before astronomers could accept the idea that these galaxies were truly ancient, they needed to answer one simple question: how far away are they? That question sounds straightforward, but measuring distance in the universe is one of the hardest problems in astronomy. There are no cosmic rulers stretched across space, no markers placed between galaxies. Everything scientists know about distance comes from interpreting light. Every photon arriving at a telescope carries information about where it came from, but that information must be decoded carefully. Picture standing on a quiet road at night. A car appears in the distance. At first, its headlights are faint. As it moves closer, the lights grow brighter and the color becomes clearer. Your brain automatically estimates distance from those changes. Astronomers do something similar with galaxies, but instead of watching objects approach, they study light that has traveled across billions of years. And the most important clue hidden inside that light is something called redshift. The concept begins with the expansion of the universe. According to modern cosmology, space itself has been stretching ever since the moment described by the Big Bang Theory. Galaxies are not flying outward through empty space like fragments from an explosion. Instead, the space between galaxies is expanding. Imagine drawing dots on the surface of a balloon. As the balloon inflates, the dots move farther apart. None of the dots are moving across the surface themselves. The surface itself is stretching. The universe behaves in a similar way. As space expands, the light traveling through it also stretches. Short wavelengths become longer. Blue light shifts toward red. Scientists call this stretching cosmological redshift. The greater the redshift, the farther the light has traveled. And the further the light has traveled, the earlier in cosmic history it was emitted. Think about waves rolling across an ocean. When waves spread out, the distance between crests grows larger. The same thing happens to light as it moves through expanding space. By measuring how much the wavelength is stretched, astronomers can estimate how far away a galaxy is. This method has become one of the most powerful tools in observational astronomy. But measuring redshift is not always simple. The light arriving from extremely distant galaxies is incredibly faint. Often only a few photons reach our instruments after traveling billions of years through space, and those photons are shifted far into the infrared range. This is exactly why the James Webb Space Telescope was built. Webb's instruments are designed specifically to detect faint infrared light with extraordinary precision. Its sensors can capture signals that older telescopes could barely see. So when Webb began identifying candidate galaxies from the early universe, astronomers immediately began measuring their redshift. Some of the first estimates came from a method known as photometric redshift. In simple terms, scientists measure how bright a galaxy appears in several different wavelength filters. By comparing those brightness patterns with theoretical models, they can estimate how far the galaxy might be. Photometric redshift is fast, but it is also uncertain. For the most important discoveries, astronomers prefer a more precise technique called spectroscopic redshift. This method breaks light into a detailed spectrum, similar to how a prism spreads sunlight into a rainbow. Inside that spectrum, specific chemical elements produce recognizable patterns of lines. Hydrogen produces one set of lines, oxygen produces another, These patterns act like fingerprints. When the entire pattern shifts toward longer wavelengths, astronomers can measure exactly how much stretching occurred. That shift reveals the galaxy's redshift with far greater accuracy, so researchers began targeting the strange early galaxies with Webb spectroscopic instruments. They wanted to confirm whether the distances were real. Picture the atmosphere inside an observatory during this stage. Teams of scientists around the world watching incoming data, running calculations, comparing spectra, waiting for confirmation, because if the redshift measurements held up, the implications would be enormous. One by one, the results began to arrive. Several candidate galaxies showed redshift values greater than z=10. Pause and think about that number for a moment. In astronomy, redshift values above 10 correspond to a time when the universe was less than 500 million years old. That is extremely early. At that stage, the first stars had only recently begun to illuminate the cosmos. And yet, Webb appeared to be detecting galaxies already containing massive numbers of stars. Imagine discovering a forest only days after the first seeds were planted. That was the scale of the puzzle. Scientists examined the measurements carefully. They cross-checked independent data sets. They repeated analyses using different methods. Again and again, the results pointed in the same direction. These galaxies truly were incredibly distant. Their light had been traveling toward Earth for more than 13 billion years, which meant the galaxies themselves existed when the universe was still in its cosmic childhood. Now pause for a moment and picture the timeline. The universe begins. For hundreds of millions of years, matter gathers slowly. Stars ignite. Small galaxies form. That was the expected sequence, but Webb's observations suggested something else. Large galaxies already existed much earlier than predicted, and that realization created a difficult question. If galaxies of that size were present so soon after the beginning, then how did they form so quickly? Gravity alone should not have had enough time to assemble such massive structures. Gas clouds need time to collapse. Stars need time to ignite. Galaxies need time to merge and grow. Yet somehow, the early universe seemed to be accelerating this process. Some astronomers began describing the situation as a timing problem. The universe appeared to be building structures faster than the models allowed. And that meant one of two things had to be wrong. Either scientists were misunderstanding the observations, or the universe itself had behaved differently than the models predicted. But as the number of confirmed early galaxies continued to grow, the second possibility began to feel more serious, because Webb was not finding just one strange object. It was finding many, and each one seemed to suggest the same unsettling idea. The early universe might have been far more efficient at building galaxies than anyone expected, which meant astronomers now faced a deeper mystery. What process could have accelerated cosmic growth so dramatically? Because if the standard explanation was incomplete, then the universe still had secrets left to reveal. When the distance measurements began to hold up, the conversation inside astronomy started to change. At first, many scientists hoped the strange galaxies would turn out to be rare exceptions. Perhaps a few unusual systems had formed early under special conditions. But the deeper researchers looked into the data from the James Webb Space Telescope, the more examples began to appear. The pattern was repeating. Galaxies were showing up earlier than expected, and some of them looked surprisingly large. To understand why this was such a problem, it helps to think about how galaxies normally grow. Picture a small snowball rolling down a snowy hill. At first it is tiny. As it moves, it gathers more snow. The snowball grows slowly, layer by layer. Galaxies grow in a similar way. Gas falls inward under gravity. Stars ignite. Small galaxies merge together. Over time, the structure becomes larger and more complex. But the key word in that process is time. Building billions of stars requires enormous amounts of gas and long periods of star formation. Even under ideal conditions, The process should take hundreds of millions or billions of years. Yet Webb's early observations seemed to show galaxies that had already completed much of that growth. Imagine walking into a forest and discovering fully grown trees where seeds were planted only a few months earlier. Something about the timeline would feel wrong. Astronomers began examining one possible explanation. Perhaps these galaxies only appeared massive because they were producing stars at extraordinary rates. Young stars are extremely bright. A galaxy experiencing a burst of rapid star formation can shine far more intensely than a quiet galaxy of similar mass. Think of fireworks exploding in the night sky. For a moment, the sky becomes brilliant with light. But the brightness does not last. If early galaxies were forming stars in enormous bursts, they might look larger than they really were. This idea gave scientists some hope. Maybe the galaxies were not truly massive yet. Maybe they were simply going through short-lived phases of intense brightness. To test this possibility, astronomers began analyzing the colors of the galaxies detected by Webb. Different types of stars emit different wavelengths of light. Young, massive stars burn hot and blue. Older stars glow with redder light. By studying the colors of distant galaxies, scientists can estimate the types of stars they contain and how long those stars have been forming. This method acts like reading the growth rings of a tree. Each generation of stars leaves a signature in the galaxy's light. When researchers examined Webb's early galaxy candidates, they expected to see signs of extremely young star populations, and some of them did. But in several cases, the data suggested something more complicated. Some galaxies appeared to contain stars that had already been forming for significant periods of time. In other words, they did not look like brand new systems. They looked more mature. Now pause for a moment and imagine the implications. If those galaxies truly contained older star populations, that would mean star formation must have begun even earlier than Webb was detecting, which pushes the timeline of galaxy formation further back toward the very beginning of cosmic history. That possibility began to attract serious attention. Some researchers suggested that the early universe might have been far more efficient at turning gas into stars. Perhaps the conditions shortly after the Big Bang allowed gas clouds to collapse faster than current models predicted. The early cosmos was different from the universe we see today. It was denser, hotter, and filled with enormous reservoirs of hydrogen gas. Those conditions might have allowed gravity to pull matter together more quickly than scientists previously believed. Think about a crowded room where people are standing close together. If someone begins moving toward the center, others quickly follow. The movement spreads rapidly through the group. In a sparse room, the same process would take much longer. The early universe may have behaved like that crowded room. Matter was packed closer together. Gravity could act more efficiently. Gas clouds might have collapsed faster, igniting stars sooner than expected. But even with faster star formation, another problem remained. Some of the galaxies Webb detected appeared not only bright but also extremely compact and dense. Their estimated masses suggested billions of stars contained within relatively small regions of space. Building that much structure requires enormous gravitational organization, and gravity alone does not act instantly. It pulls matter together gradually. Astronomers began running new computer simulations to test whether faster star formation could reproduce the Webb observations. Simulations are powerful tools. Scientists program physical laws, gravity, gas dynamics, radiation into supercomputers, and let them simulate billions of years of cosmic evolution. The simulations start with conditions measured in the cosmic microwave background, the ancient radiation left over from the early universe. From there, they watch virtual galaxies grow over time. These simulations have successfully reproduced many features of the modern universe. They predict the distribution of galaxies across space. They explain the large-scale cosmic web of filaments and clusters. But when scientists tried adjusting the simulations to match Webb's early galaxies, the results were mixed. some models could produce slightly larger galaxies earlier in cosmic history. But producing large numbers of massive galaxies within the first few 100 million years remained difficult. The models still struggled to match what Webb appeared to be seeing. At this stage, astronomers started using a phrase that appears often in science when observations challenge theory: cosmic tension. This does not mean the existing model is necessarily wrong, but it means there is a mismatch between predictions and observations, and when that mismatch appears, scientists must investigate carefully. Sometimes the observations improve, sometimes the models evolve, sometimes the both. Now here is where the story becomes even more interesting. The Webb discoveries were not only raising questions about galaxy growth, they were also pointing towards something deeper, because galaxies do not form alone. Their growth is guided by something invisible, something that shaped the structure of the entire universe. And to understand why early galaxies might have formed faster than expected, scientists had to look closely at the hidden framework of the cosmos itself. A framework made of something we cannot see, something known as dark matter. And that invisible substance might hold the next clue in this unfolding mystery. By the time astronomers reached this point in the investigation, one idea kept returning to the center of the discussion: dark matter. It is one of the strangest concepts in modern science. We cannot see it, we cannot touch it. No telescope has ever captured a direct image of it, and yet almost everything in the universe appears to depend on it. To understand why, picture a carousel spinning slowly in a playground. Children sit along the outer edge. As the carousel spins faster, the outward pull becomes stronger. If nothing held the children in place, they would slide off the edge. Galaxies behave in a similar way. Stars orbit the centers of galaxies at enormous speeds, according to the gravity produced by visible matter alone. Those stars should not be able to stay in orbit. They should fly outward into space. But they don't. Instead, galaxies hold together as if there is far more mass present than we can see. Astronomers discovered this mystery decades ago by measuring how fast stars move around galaxies. The speeds were too high for the visible matter alone to explain. Something else had to be there, something invisible. That invisible mass became known as dark matter. Today, scientists estimate that dark matter makes up about 85% of all matter in the universe. Ordinary matter, the atoms forming stars, planets, and people, represents only a small fraction of the total. But dark matter does not interact with light. It does not glow. It does not absorb radiation. Its presence is revealed only through gravity. Now pause for a moment and picture the universe on its largest scale. Instead of isolated galaxies floating randomly through space, imagine an enormous cosmic web. Long filaments of matter stretch across billions of light years. Where these filaments intersect, giant clusters of galaxies appear. Between the filaments lie enormous empty regions called cosmic voids. This vast structure is shaped largely by dark matter. Scientists believe dark matter began clumping together very early in cosmic history. Those clumps formed invisible gravitational wells. Ordinary gas then flowed into those wells, and inside those dense regions, the first stars and galaxies were born. Think of dark matter like the hidden framework of a building. Before walls and windows appear, builders construct the steel skeleton that supports the structure. Once the framework exists, everything else grows around it. Dark matter provides the universe with a similar skeleton. Without it, galaxies might never have formed at all. This idea is supported by powerful computer simulations. When scientists simulate the universe using only ordinary matter, galaxies fail to form in the correct patterns. But when dark matter is included, the simulations begin to resemble the real cosmic web observed by telescopes. So dark matter has become one of the cornerstones of modern cosmology. But here is where the Webb discoveries begin to complicate things. If galaxies appeared earlier than expected, then perhaps the dark matter structures that helped create them also formed earlier. Remember the snowball analogy from earlier. Galaxies grow by collecting gas and merging with other galaxies, but they need gravitational wells to start the process. Dark matter halos provide those wells. If those halos formed sooner in the early universe, they could have accelerated galaxy formation. Imagine planting seeds in deep soil instead of shallow ground. The deeper soil gives roots more room to grow quickly. Plants might appear much sooner than expected. In the same way, if dark matter halos formed earlier and grew larger faster, galaxies could have begun forming stars much sooner. Some astronomers began exploring this possibility. They examined whether dark matter might behave slightly differently under early cosmic conditions. Perhaps it combed more rapidly. Perhaps the density fluctuations in the young universe were larger than expected. Even small changes in these early conditions could significantly affect how quickly structures form. But adjusting dark matter behavior is not simple. The existing model of dark matter has successfully explained many features of the universe. Galaxy rotation curves, large-scale cosmic structure, gravitational lensing patterns. All of these observations fit remarkably well with the current understanding of dark matter. Changing the model too drastically could disrupt those successful predictions, so researchers had to proceed carefully. They tested alternative ideas. Some explored whether a slightly different type of dark matter particle might allow structures to grow earlier. Others examined whether early cosmic conditions allowed dark matter halos to collapse more efficiently. Each new simulation attempted to recreate the galaxies that Webb was observing. Some models came closer than before, but many still struggled to produce galaxies as massive and numerous as those appearing in Webb's deep images. That meant another possibility had to be considered. Perhaps the earlier stars themselves behaved differently. After all, the first stars formed in an environment very different from today's universe. They were born from pure hydrogen and helium, without the heavier elements that later generations of stars contain. Those early stars might have been far larger than modern stars. Some theoretical models suggest the first stars could have reached hundreds of times the mass of our Sun. Massive stars burn hotter. They release enormous amounts of energy. They can collapse quickly and trigger the formation of additional stars nearby. If early stars formed in these extreme conditions, entire galaxies might have ignited far more rapidly than expected. This possibility was already being explored by astrophysicists studying the earliest stellar populations. But Webb's discoveries gave these ideas new urgency. Because if the first stars were indeed larger and more powerful than predicted, they could have dramatically accelerated the growth of galaxies, and that would shift the entire timeline of cosmic evolution. But even this explanation faced limits. Extreme star formation alone might not be enough to account for the surprisingly large galaxies Webb appeared to detect, which meant the mystery remained unresolved. Something in the early universe seemed to be pushing galaxy formation forward faster than our models allowed, and that realization led scientists to the next step in the investigation. They turned back to their most powerful tools, not telescopes, but simulations. Massive digital universes running inside supercomputers, and when those simulations were compared with Webb's observations, something unexpected began to happen. The models started to break. For decades, computer simulations have been one of the most powerful tools in modern astronomy. Scientists cannot watch galaxies grow in real time. The process takes billions of years. No telescope can observe the full life of a galaxy from birth to maturity. But computers allow researchers to recreate that process. Inside powerful supercomputers, scientists build digital versions of the universe. They program in the laws of physics, gravity, gas motion, radiation, and the effects of dark matter. Then they press start. The simulation begins with conditions similar to those measured in the early universe, especially the tiny density patterns seen in the cosmic microwave background. From there, the virtual universe evolves. Gas collapses, stars ignite, galaxies form. Over billions of simulated years, these models build cosmic structures that can be compared with real observations. Think of it like building a digital weather system. Meteorologists simulate clouds, wind, and temperature patterns to predict storms. Astronomers simulate gravity, matter, and energy to predict galaxies. And for many years, the results were impressive. Simulations reproduced many of the large-scale patterns seen across the universe. They produced vast cosmic filaments stretching across millions of light-years. They formed clusters of galaxies where those filaments intersect. They even predicted the sizes and shapes of many galaxies observed by telescopes like the Hubble Space Telescope. In many ways, the models seemed to work. But models are always tested against new data. And when the James Webb Space Telescope began revealing galaxies from the earliest periods of cosmic history, scientists quickly compared those observations with their simulations. At first, the expectation was simple. The models should match the new observations fairly well. Maybe a few adjustments would be needed, but overall, the predictions should hold. Instead, researchers started seeing something troubling. The simulated universes were producing far fewer large galaxies than Webb appeared to detect, and the galaxies that did form early were usually much smaller than the ones Webb was observing. Picture running a weather simulation that predicts gentle rain, then stepping outside and discovering a hurricane. That kind of mismatch demands attention. Astronomers began testing their models again. They adjusted parameters. They increased the efficiency of star formation. They changed assumptions about how gas cools and collapses. Each adjustment was meant to see whether galaxies could grow faster in the early universe. Some changes helped. Simulated galaxies could become slightly larger, slightly earlier, but many models still struggle to produce galaxies as massive as those suggested by Webb's observations. The timeline simply seemed too short. Remember, many of these galaxies appear only about 300 to 500 million years after the Big Bang. In cosmic history, that is an extremely narrow window. To build a galaxy containing billions of stars within that time requires extraordinary conditions. Imagine building an entire city in a matter of weeks. You would need massive resources, perfect coordination, and incredibly fast construction. The universe appeared to be doing something similar, yet the simulations could not easily reproduce it. This is where the phrase cosmic tension began appearing more frequently in scientific discussions. Cosmic tension does not mean scientists believe the entire model of the universe is wrong. Instead, it signals that observations and predictions are not lining up perfectly. And when that happens, researchers begin searching for missing pieces. Sometimes the missing piece is a new physical process that was not included in the simulation. Sometimes the observational data improves with time and resolves the discrepancy. And sometimes the tension leads to deeper revisions in our understanding of how the universe works. At this stage, scientists were not abandoning the current model of cosmology, but they were paying very close attention, because Webb's observations were not just a single unusual result. More data continued arriving. New deep field surveys, new galaxy candidates, new redshift measurements. And the same pattern kept appearing. Large galaxies were showing up surprisingly early. Astronomers began exploring several possibilities. Maybe the first stars formed even faster than expected. Maybe early galaxies merged together at unusually high rates. Maybe dark matter halos collapsed earlier than the simulations predicted. Each idea was tested carefully. Each simulation was rerun. And in some cases, the models improved slightly. But the tension did not disappear. Picture trying to solve a puzzle where several pieces seem to be missing. You can still see part of the image, but the full picture refuses to come together. That is where the study of early galaxy formation now stood. Scientists had powerful telescopes. They had detailed simulations. They had decades of theoretical research. And yet the early universe was still revealing surprises. Now pause for a moment and consider something important. Whenever science encounters unexpected results, two possibilities always exist. The observations could be misleading, or the theory could be incomplete. History shows examples of both. Sometimes early measurements turn out to be mistaken. Other times, surprising observations open the door to entirely new discoveries. At this stage, astronomers were carefully testing both possibilities. More observations were needed, more measurements, more data. But there was another area of research that could help explain the mystery. It involved the very first generation of stars. Stars unlike any that exist today. Stars that may have burned brighter, lived faster, and changed the early universe in dramatic ways. If those early stars behaved differently than scientists expected, they might have accelerated the formation of galaxies across the young cosmos. And that possibility led researchers deeper into the study of the universe's first stellar giants. Because the earliest stars may have been far more powerful than anything we see in the sky today, to understand how galaxies could appear so early, astronomers began looking deeper into the story of the first stars. Because before galaxies can exist, stars must ignite. Stars are the engines that shape galaxies. They create light, heat, and the heavier elements needed to build planets and complex chemistry. Without stars, galaxies would simply be clouds of cold gas drifting through space. But the first stars were born in a universe very different from the one we see today. Pause for a moment and imagine the cosmos shortly after the beginning described by the Big Bang Theory. There were no planets, no heavy elements, no carbon, oxygen, or iron. The universe contained almost nothing but hydrogen and helium. These simple atoms filled enormous clouds stretching across space. Gravity slowly pulled parts of those clouds inward, compressing the gas until temperatures rose high enough for nuclear fusion to begin. And when fusion begins, a star is born. But here is the key detail. Modern stars form from gas that contains many different elements. Over billions of years, earlier generations of stars have enriched the universe with heavier materials. Those elements help gas clouds cool efficiently, allowing them to fragment into many smaller stars. The first stars did not have that advantage. Their gas clouds were simpler and hotter. Without heavy elements to help cooling, the collapsing clouds may have formed much larger stars. Think about baking bread. If the dough breaks into many small pieces, you end up with many small rolls. But if the dough stays together as one large mass, you get a single large loaf. Early star-forming clouds may have behaved more like that single loaf. Instead of forming many small stars, they may have produced a few extremely massive ones. Astronomers call these early stars population 3 stars. These stars have never been directly observed. They existed so early in cosmic history that they likely burned out long before the universe reached its current age. But theoretical models suggest they may have been enormous. Some estimates suggest mass is 100 times greater than our Sun. Others suggest even larger. Stars that massive burn through their nuclear fuel extremely quickly. A star like our Sun will live for about 10 billion years. A star hundreds of times more massive might live only a few million years. But during that short life, it releases enormous amounts of energy. Picture a giant bonfire compared with a small candle. The bonfire burns hotter, brighter, and consumes its fuel much faster. If the early universe produced large numbers of these massive stars, entire regions of space could have lit up quickly. Those stars would flood surrounding gas with radiation, triggering the formation of additional stars nearby. Some would collapse into massive black holes when they died. Others would explode in violent supernovae, scattering newly formed elements into surrounding space. Those explosions could compress nearby gas clouds, causing new waves of star formation. In other words, the first stars might have accelerated cosmic evolution dramatically. Think of a chain reaction. One massive star ignites. Its radiation compresses nearby gas. More stars form. those stars explode and trigger additional star formation. The process spreads across a region of space like sparks spreading through dry grass. If that chain reaction occurred across many early galaxies, star formation could have advanced much faster than scientists once expected. Now pause and think about how that connects to the galaxies observed by the James Webb Space Telescope. If the earliest stars were extremely massive and triggered rapid waves of star formation, galaxies might have built their stellar populations much faster. A system that normally takes 1 billion years to assemble could potentially grow in a few hundred million. That possibility caught the attention of many researchers studying Webb's discoveries. Some began revisiting older models of population 3 stars. Could they have been even larger than previously believed? Could they have formed in greater numbers? Could their radiation and explosions have reshaped early galaxies more rapidly? Computer simulations began incorporating these possibilities. Researchers tested scenarios where early stars formed in enormous bursts. They simulated galaxies experiencing intense periods of star formation far greater than what we observe today. Some of these simulations began producing galaxies that looked more similar to the ones Webb was detecting. Brighter, larger, more developed. But even this explanation had limits. While massive early stars could accelerate star formation, they might still struggle to build galaxies containing billions of stars within such a short cosmic window. The timeline remained tight. There simply might not have been enough time. And this raised another intriguing possibility. Perhaps something else in the early universe was also growing faster than expected, something even more powerful than stars. Something that sits at the center of many galaxies today. Something capable of reshaping entire galaxies through its gravity. Black holes. These objects are usually associated with extreme environments, regions, where gravity becomes so strong that not even light can escape. Many galaxies contain supermassive black holes at their centers. Our own Milky Way galaxy hosts one called Sagittarius A. But astronomers once believed that such enormous black holes took billions of years to grow. Now Webb was beginning to suggest something surprising. Some black holes might have appeared far earlier than expected, and if that was true, they could be playing an important role in the rapid growth of early galaxies. Because black holes do not just sit quietly at the centers of galaxies, they can shape their surroundings in powerful ways. And the deeper astronomers looked into Webb's data, the more signs they began to find that these cosmic giants may have appeared much sooner than anyone predicted. For many years, astronomers believed they understood how large black holes grow. The process seems simple in principle. A star collapses, gravity compresses its core. If the remaining mass is large enough, the collapse becomes unstoppable. The object shrinks until it forms a region where gravity becomes so intense that not even light can escape. That object becomes a black hole. Most black holes form this way begin relatively small, perhaps a few times the mass of the Sun. From that starting point, they grow slowly. Gas falls inward, stars drift too close. Occasionally, two black holes merge together. Over long periods of time, the black hole gains mass. But here is the important detail. Growth takes time. Even under ideal conditions, black holes cannot grow infinitely fast. There are physical limits on how quickly matter can fall inward without radiation pushing the gas away again. Astronomers call this limit the Eddington rate. Imagine trying to pour water into a funnel. If you pour slowly, the water flows smoothly through the narrow opening, but if you pour too quickly, the funnel overflows. Black holes behave in a similar way. Gas falling inward becomes extremely hot and bright. The radiation pushing outward can slow the inflow of additional matter. This natural balance limits how quickly a black hole can grow. Because of this limit, scientists believe that the enormous black holes found in modern galaxies must have taken billions of years to reach their current sizes. For example, at the center of our galaxy sits a black hole known as Sagittarius A. It contains roughly 4 million times the mass of our Sun. In other galaxies, black holes can be even larger, billions of times the mass of the Sun. Those giants were assumed to be the result of long periods of slow growth, but when astronomers began examining the early universe more closely, a surprising pattern emerged. Even before the launch of the James Webb Space Telescope, earlier surveys had detected extremely distant quasars. Quasars are galaxies with actively feeding supermassive black holes at their centers. As gas falls toward the black hole, it forms a glowing disk that can shine brighter than the entire galaxy around it. Some of these quasars were already visible when the universe was less than 1 billion years old. That discovery was already difficult to explain. To grow a black hole containing 1 billion solar masses within such a short time required extremely efficient feeding. Now Webb was pushing observations even earlier into cosmic history, and new data suggested that black holes might have appeared much sooner than expected. In several distant galaxies observed by Webb, astronomers began detecting unusual energy signatures. These signals hinted that powerful central objects might already be present, objects that could be early black holes. Pause for a moment and imagine what that would mean. If black holes existed in the centers of galaxies only a few 100 million years after the Big Bang, their growth must have started incredibly early, perhaps even earlier than the formation of the galaxies themselves. Some researchers began exploring an idea known as direct collapse black holes. In this scenario, enormous clouds of gas collapsed directly into massive black holes without first forming stars. Imagine a giant whirlpool forming suddenly in a calm ocean. Instead of building gradually from small disturbances, the entire structure appears quickly. If conditions in the early universe allowed massive gas clouds to collapse this way, the resulting black holes could begin their lives already containing thousands or even millions of solar masses. From that starting point, further growth would be much easier. And these early giants could dramatically influence their surroundings. Black holes affect galaxies in powerful ways. As matter falls toward them, enormous amounts of energy are released. Jets of high-energy particles can shoot outward across thousands of light years. Radiation can heat nearby gas clouds. Sometimes that radiation slows star formation. Other times the shock waves from black hole activity compress gas and trigger new bursts of star birth. In other words, black holes can shape the evolution of entire galaxies. If large black holes appeared early in cosmic history, they might have helped accelerate the growth of galaxies around them. Picture a powerful engine sitting at the center of a developing city. Its energy spreads outward, shaping the environment and influencing how the city grows. Early black holes may have played a similar role. But once again, astronomers faced the same challenge. The timeline remained tight. Even with direct collapse models, producing large black holes so early requires specific conditions. Gas clouds must collapse without fragmenting into stars. Radiation from nearby stars must prevent cooling at the wrong moment. Gravity must compress enormous amounts of matter very quickly. These events might occur. But how often? Could they explain the number of early galaxies Webb appeared to detect? The investigation continued. Astronomers combined observations from Webb with data from other observatories. They examined the brightness patterns of distant galaxies. They searched for spectral signatures indicating black hole activity. Some results supported the idea. Others remained uncertain. Science rarely provides immediate answers. Instead, it builds understanding step by step. And as the Webb telescope continued collecting new observations, astronomers began noticing something that made the mystery even deeper. The number of early galaxies appearing in the data seemed larger than expected. Not just one or two unusual objects, but many. And that raised a difficult possibility. What if the issue was not just early stars or early black holes? What if something about the entire timeline of cosmic history needed to be reconsidered? Because if galaxies formed earlier than predicted, then perhaps our picture of the early universe was still incomplete. And that possibility would lead scientists to ask one of the most uncomfortable questions in cosmology. Could the timeline of the universe itself be slightly different than we thought? By this stage of the investigation, astronomers had ruled out many of the simpler explanations. The galaxies detected by the James Webb Space Telescope appeared to be real. Their redshift measurements suggested enormous distances. Their brightness and structure hinted at large populations of stars, and similar objects were appearing in multiple observations. This forced scientists to confront a more difficult question. What if the timeline of the early universe needs adjustment? Now pause for a moment before jumping to conclusions. This does not mean the age of the universe itself is suddenly in doubt. The current estimate, about 13.8 billion years, comes from several independent measurements, including the detailed patterns seen in the cosmic microwave background. Those measurements remain extremely strong. But the sequence of events within the early universe might still contain surprises. Think of history books describing the growth of a city. Historians might know the city's founding date very precisely, but the exact timing of when certain neighborhoods developed, when industries appeared, or when major buildings were constructed might still be debated. Cosmic history works in a similar way. Scientists know when the universe began expanding. They know when atoms formed. They know when the first light of the cosmic microwave background was released, but the exact timeline of galaxy formation may still contain unknown chapters. For decades, cosmologists believed that large galaxies required long periods of gradual growth. Small galaxies formed first, then mergers slowly built larger systems. Over billions of years, massive galaxies emerged. This model fit most observations reasonably well, but Webb's discoveries were beginning to suggest that the early universe might have been more active than predicted. Galaxies seemed to appear quickly. Stars ignited rapidly. Structures developed sooner. Now picture planting a forest. If the soil, sunlight, and water are perfect, the trees might grow faster than expected. But they still cannot grow overnight. There are biological limits. The same is true for galaxies. Gravity pulls gas together. Stars ignite. Energy spreads through the system. Each stage takes time. The surprising part of Webb's observations is how quickly these stages seem to have occurred. Some galaxies appear to have assembled billions of stars within only a few 100 million years after the Big Bang Theory. That leaves a very narrow window for the entire process. Scientists began considering several possibilities. One idea suggested that the earliest galaxies might be forming stars far more efficiently than modern galaxies. In our current universe, only a small fraction of gas in a galaxy turns into stars at any given time. But the early universe may have been different. Gas was denser. Galaxies were smaller. Gravitational interactions were more frequent. Under those conditions, star formation might have been much more intense. Another possibility involves the nature of dark matter halos. If the invisible structures made of dark matter formed earlier than predicted, they could have provided deeper gravitational wells where gas could gather quickly. That would allow galaxies to begin forming sooner. Some researchers also began exploring whether our measurements of early galaxy masses might be slightly misleading. When astronomers estimate the mass of distant galaxies, they rely on the light produced by stars. But if early stars were extremely massive and unusually bright, they might make galaxies appear heavier than they truly are. Imagine trying to estimate the size of a crowd by the brightness of its flashlights. If everyone suddenly turns on a powerful spotlight instead of a small flashlight, the crowd might appear much larger than it really is. In a similar way, the brightness of early stellar populations might distort our estimates of galaxy mass. But even with these possibilities, the tension remains. Some galaxies still appeared surprisingly developed for their age. This led to a broader realization among cosmologists. Our current models of galaxy formation may still be missing some important ingredients. That realization is not unusual in science. Throughout history, new instruments have often revealed unexpected details about the universe. The telescope of Galileo Galilei revealed moons orbiting Jupiter, radio telescopes uncovered mysterious pulsars. Space telescopes revealed thousands of distant galaxies invisible from Earth. Each new instrument opened another layer of cosmic discovery. The Webb telescope is simply the newest and most powerful tool in that long tradition, and like many revolutionary instruments before it, Webb is revealing surprises, but science rarely moves through sudden collapse of existing theories. Instead, it evolves. New observations refine old models. Better measurements replace uncertain ones. Ideas are tested, revised, and tested again. At the moment, astronomers are in the middle of that process. The early universe appears more complicated than once believed. Galaxies may have formed earlier. Stars may have burned brighter. Black holes may have grown faster. Each of these possibilities is now being explored, and with every new observation from Webb, the picture becomes a little clearer. But the deeper scientists look into the early universe, the more one idea begins to emerge. The cosmic dawn, the era when the first galaxies ignited, may have been far more dramatic than we once imagined. Instead of a slow sunrise, it may have been more like a sudden blaze of light across the universe. And if that is true, it means we're only beginning to understand how quickly the cosmos began building the structures we see today. Because Webb's discoveries are not just rewriting details, they are revealing a universe that may have grown up faster than anyone expected. When observations challenge long-standing expectations, science does not stop. It adapts. Astronomers began proposing new ideas to explain the galaxies appearing in the early images from the James Webb Space Telescope. These ideas were not wild guesses. Each one had to fit the laws of physics, match previous observations, and survive careful testing. Still, something clearly needed explanation, because the galaxies Webb revealed were appearing earlier than many models predicted, so researchers began asking a different question. What if the early universe had conditions that allowed galaxies to grow unusually fast? To explore that idea, scientists returned to the basic ingredients that create galaxies: gravity, gas, dark matter, and stars. Each of these ingredients could potentially behave slightly differently during the universe's earliest period. Let's start with gas. The early universe contained enormous clouds of hydrogen gas. These clouds were far denser than the gas we see scattered across galaxies today. Picture fog filling an entire valley. If the fog thickens enough, water droplets begin to collect quickly. Something similar may have happened in the early universe. Dense gas clouds could collapse rapidly under gravity. When enough gas gathers in one place, pressure rises. Eventually, the temperature becomes high enough to ignite nuclear fusion. A star is born. If this collapse happened more efficiently in the early universe, entire clusters of stars could form quickly. And where many stars appear, galaxies begin to emerge. Some new models suggest that early gas clouds might have been able to collapse much faster than previously assumed. This would allow galaxies to accumulate mass earlier in cosmic history, but gas alone cannot explain the entire puzzle. The second ingredient, dark matter, may also play an important role. As we discussed earlier, dark matter forms invisible halos that guide where galaxies develop. These halos act like gravitational bowls where gas collects and cools. If dark matter halos formed earlier than predicted, they could have created the conditions for galaxy formation much sooner. Imagine building houses on prepared foundations. If the foundations appear earlier, construction can begin earlier. Some simulations now explore scenarios where dark matter structures collapse sooner than standard models predicted. Even a small change in timing could allow galaxies to begin forming stars tens of millions of years earlier. That might not sound like much, but in the early universe, tens of millions of years can make a huge difference. Now consider the third ingredient, stars. The earliest stars, often called population 3 stars, may have behaved differently than modern stars, without heavy elements to help cool the gas around them. These stars may have grown extremely large. Large stars burn hotter, and produce enormous radiation. Their intense energy could trigger additional star formation in nearby regions. Think about sparks spreading through dry grass. One flame can ignite several others. If the early universe contained many such massive stars, entire galaxies could ignite quickly. Some astronomers now believe these early starbursts might have been far more intense than anything we observe today. That could explain why some early galaxies appear brighter than expected. But there is another factor scientists are studying carefully: mergers. Galaxies grow not only by forming new stars but also by colliding and merging with one another. When two galaxies merge, their stars combine, their gas clouds compress, and new waves of star formation often ignite. The early universe was smaller and denser. Galaxies were closer together. That means collisions may have been more common. Picture a crowded intersection in a busy city. When traffic is dense, encounters happen frequently. In the same way, early galaxies might have merged often, building larger systems faster than expected. Simulations now show the frequent early mergers could help explain the rapid growth Webb is revealing. But even these combined explanations may not solve every part of the puzzle. Some galaxies detected by Webb still appear unusually large for their estimated age, and that keeps astronomers cautious. Science works best when explanations are tested carefully. Researchers will continue measuring redshifts. They will study the chemical fingerprints of early galaxies. They will search for signs of the first stars, and they will run ever more detailed simulations. The important thing to understand is that this process is normal. Every major scientific discovery creates new questions. When the first radio telescopes discovered pulsars, scientists were confused by the strange signals. When astronomers first detected cosmic microwave background radiation, they realized it confirmed a major theory about the universe's origin. Each discovery reshaped our understanding. The same process may now be happening again. The Webb telescope has opened a window into a part of cosmic history that was previously hidden, and what it is showing us is both fascinating and surprising. The early universe may have been far more active than scientists once imagined. Galaxies may have formed quickly. Stars may have ignited in enormous bursts. Black holes may have grown earlier than expected. But this is only the beginning of the investigation, because the deeper Webb looks, the more evidence begins to suggest that the first era of galaxies, the cosmic dawn, may have been a much brighter and busier place than anyone predicted, and understanding that era may change how we think about the growth of the entire universe. By now, a new picture of the early universe was slowly beginning to take shape. It was not yet complete. Many questions remained. But the growing collection of observations from the James Webb Space Telescope was revealing a consistent theme. The young universe may have been far more active than scientists once imagined. For decades, astronomers pictured the early cosmos as a slow beginning, a long, quiet build-up where small structures gradually assembled into larger galaxies. But Webb's observations hinted at something different. A faster start, a universe that began building complex structures almost immediately. To understand how surprising this is, picture the timeline of cosmic history as a single calendar year. The Big Bang occurs at midnight on January 1st. Galaxies slowly begin forming over the next months. Our own solar system appears near the end of September. Humans arrive only in the final seconds of December 31st. In that enormous timeline, the galaxies Webb is observing appeared astonishingly early. Many seem to exist when the cosmic calendar would still be somewhere in January. That means the universe was already producing large numbers of stars only a short time after its beginning. Imagine opening the doors of a new city only days after construction begins, and finding entire neighborhoods already filled with buildings. Something about the pace of development would feel unusual. Astronomers began describing this period as a more energetic cosmic dawn. Instead of a faint glow slowly spreading across the universe, it may have been closer to a rapid blaze of star formation. Large clouds of hydrogen gas collapsed quickly. the first stars ignited. Their radiation transformed surrounding space. Within a few 100 million years, entire galaxies may have appeared. That possibility changes how scientists think about the earliest era of cosmic structure. But Webb's observations also raise another interesting idea. Perhaps the early universe simply contained more raw material for galaxy formation. Remember that shortly after the Big Bang Theory, matter was distributed differently than it is today, and the universe was smaller, denser. Gas clouds were closer together. Under those conditions, gravity could act more efficiently. Picture rainfall collecting in a small valley. If the valley is narrow, the water gathers quickly. If the valley is wide, it takes longer for streams to form. The early universe may have resembled that narrow valley. Gas clouds gathered rapidly, stars ignited, galaxies assembled faster than expected. Another clue may lie in the behavior of dark matter. As we discussed earlier, invisible halos of dark matter provide the gravitational framework where galaxies grow. If those halos formed slightly earlier than predicted, they could have accelerated galaxy formation across the young universe. Simulations exploring this possibility are now being studied carefully, but even if the early universe allowed galaxies to grow quickly, there is still much we do not fully understand. Many early galaxies detected by Webb appear surprisingly bright. Some appear dense and compact. Others show signs of rapid star formation. Astronomers are now examining the chemical fingerprints inside their light to learn more. When stars form, they produce elements such as carbon, oxygen, and nitrogen. These elements leave distinct patterns in the spectra of galaxies. By studying these patterns, scientists can estimate how many generations of stars have already lived and died inside a galaxy. This is similar to studying layers of sediment in ancient rock. Each layer records part of the history. Some Webb observations suggest that even early galaxies may already contain heavier elements created by earlier stars. If that is true, it means star formation must have started even earlier than the galaxies we currently observe. And that possibility pushes the beginning of cosmic dawn even closer to the origin of the universe. Pause for a moment and imagine the scale of this investigation. Humanity has built a telescope floating nearly 1 million miles from Earth. Its mirrors capture faint infrared light that began traveling across space more than 13 billion years ago. From those tiny signals, scientists reconstruct the story of how the first galaxies formed. It is like trying to understand the construction of an ancient city by examining a few scattered stones. Every new observation adds another piece to the puzzle, and Webb is still only beginning its mission. The telescope is expected to operate for many years. Each new deep field survey will reveal additional galaxies. Some may confirm the patterns already seen. Others may challenge current ideas even further. That is the nature of exploration. Every time humanity builds a better instrument, the universe reveals something unexpected. Galileo's telescope revealed moons orbiting Jupiter. The Hubble Space Telescope revealed that the universe contains far more galaxies than once believed. And now Webb is showing us the earliest stages of galaxy formation with unprecedented clarity. The discoveries are not destroying cosmology, but they are refining it. Our understanding of the early universe is becoming more detailed, more complex, and far more interesting, because the deeper we look into cosmic history, the more we realize that the universe may have grown up faster than anyone expected. And that realization leads to a final reflection about what these discoveries mean for us. Because understanding how galaxies formed is not just a question about distant stars, it is also a story about how the universe eventually created the conditions for life, including us. Step back for a moment and think about what we have just explored. A telescope built by human hands is floating far beyond the moon, quietly observing faint light that began its journey billions of years ago. Each photon captured by the James Webb Space Telescope carries a fragment of history. a message from a time when the universe itself was young. Those messages are revealing something unexpected. Galaxies may have appeared earlier than scientists once believed. Stars may have ignited quickly. Black holes may have grown faster. And the cosmic dawn, the moment when the first structures lit the darkness, may have been far more dramatic than anyone predicted. Pause for a moment and imagine the scale of this story. The universe begins in a state of intense heat and density, described by the Big Bang Theory. Space expands, atoms form, gravity begins its slow work, pulling matter into clumps. Stars ignite, galaxies grow. Over billions of years, those galaxies create new generations of stars. Heavy elements form inside stellar cores and spread through space when stars explode. Those elements become the building blocks of planets. Planets orbit stars. On at least one of those planets, chemistry becomes biology. Life appears. Eventually, intelligent life begins asking questions about the sky. Think about how unlikely that chain of events is. The first stars had to form. Galaxies had to grow. Heavy elements had to be created. Planetary systems had to emerge. Life had to survive long enough to evolve intelligence. And that intelligence had to become curious about the universe. All of those events stretch across billions of years of cosmic history. Yet today we are able to study the earliest moments of galaxy formation, using instruments built by a species that appeared only recently on the cosmic timeline. Picture the cosmic calendar again. The universe begins on January 1. Human civilization appears in the final seconds of December 31st. And yet, in those final seconds, we have begun reconstructing the story of the entire year. That is what astronomy allows us to do. We cannot travel backward in time, but the universe sends its past toward us in the form of light. Every star in the sky is a message from an earlier moment. Every galaxy carries information about how the universe grew. And sometimes those messages reveal surprises. The galaxies discovered by Webb remind us that our understanding of cosmic history is still evolving. Science is not a fixed set of answers. It is a process. New tools reveal new data inspires new ideas, and each generation of researchers adds another layer of understanding. The Webb telescope will continue observing the deep universe for years to come. Astronomers will measure new galaxies. They will refine distance estimates. They will study the chemical fingerprints of early stars. Some of the current mysteries may eventually find simple explanations. Others may lead to deeper discoveries about the structure of the cosmos. That is the nature of exploration. Each answer opens the door to another question. But perhaps the most remarkable part of this story is not just the galaxies themselves. It is the fact that the universe has produced something capable of studying them. Out of billions of galaxies and trillions of stars, a small planet formed around an ordinary star in one spiral galaxy. On that planet, life emerged, and eventually, that life built instruments powerful enough to observe the earliest chapters of cosmic history. In a way, the universe has created a system capable of reflecting on its own origins. The atoms in our bodies were forged inside ancient stars. The light we observe traveled across billions of years to reach us. And the questions we ask today are part of the same cosmic story. We are not at the center of the universe, but we are part of it. And through curiosity, observation, and discovery, we have begun to understand how this vast cosmos came to be, a universe that formed galaxies earlier than expected, a universe still full of mysteries, and a universe that, through us, has learned to look back at itself.